is Ashleigh Henning. This is my Physics 2311 Lab 1 constant velocity. The objective of this lab is to observe and quantify the motion of an object moving at the same speed that is not changing direction. Additionally, to compare the analysis of observation versus the analysis of a computational model. The fundamental principle is observed with Newton's second law, where the change of velocity is being related to the sum of the forces over the mass of the system. A motion equation can be derived from this to predict both the velocities of the position in the future and the positions in the future. The idea of Newton's second law is that the acceleration or change in the velocity is proportional to net force and inversely proportional to the mass of the object. With the assumption that this is moving at a constant velocity, it gives crucial details in understanding the net force of the system and can be used to make predictions about the position of the system in the future. As illustrated in the second equation, the final position of the object can be known just knowing the velocity, change in time, and the initial position vector. The lab was modeled after observing the position of a marker moving across a sheet of paper. The system was defined as being only the marker, while the surroundings were everything else, including the paper, the table, the hand that pushed, and the rest of the universe. The primary results of this lab were both an observed and computational analysis of motion. The observed model, which was analyzed by tracker, predicted the velocity of the marker to be 0.0492 meters per second, while the computational model had a predicted velocity of 0.034 meters per second. The initial position vector was defined to be 4.063 times 10 to the negative 3 meters in the x direction, and this was defined by the calibration of a point mass in tracker. This was also defined in our code that we ran in our initial position vector. Let's unpack the observational analysis of motion. After graphing these positions over time, the linearization of data, gave insight to the velocity of the marker. The slope of the line is 0.0492 meters per second, which is equivalent to the object's velocity. From this equation, predictions of the object's position can be made, such as at time 100 seconds, given that the object continued to move without any external forces, the position would be expected to be 4.9313 meters in the x direction. Let's look at the computational analysis of the object's motion. When the loop is run, the object's position vector is changed by accounting for the object's initial position and increasing the velocity times the change in time. This led to the creation of the second line in the graph. This line indicates that the velocity is 0.034 meters per second. Predictions of the object's position can be made as well. Following the past example, at time 100 seconds, the position would be expected to be 3.4041 meters in the x direction. There are several similarities and differences between the models, as they are both able to predict a linear relationship between distance and time. However, these lines do not perfectly overlap, and this can be explained by the experimental errors within this lab. The experimental errors primarily impact the observational model of motion. This is because there could be a F net of being 0 due to drafts in the room or unaccounted friction on the paper that cause more force than accounted for in the models. To describe the pushes and pulls of the model, as explained earlier, Newton's second law gives context to the net forces acting on the system. Knowing the potential major contributors of force are likely weight, initial push, and friction, and also knowing the position versus time of the object was linear, Newton's law can describe a zero net force on the system. However, knowing the pushes and pulls in the model can be difficult because of random errors, like mentioned earlier, with a draft in the room that could be present, causing additional forces that are acting on the object. The orientation of the model had it moving towards the right being the positive direction. If this were to be interchanged, the results of the model would be the exact same. The object would still be moving at a constant velocity with the same magnitude, and the model would still be able to predict the position of the object. However, the direction of the velocity would swap. The usage of Newton's second law is best applied in situations of this extent. Primarily, it is known that the object is going to be moving at a constant speed without changing direction. Because the analysis of the object was looking only for the position and velocity, Newton's second law sets a perfect stage for the scheme of this problem. Thank you.